Okay, Assalamualaikum and good morning. So we'll continue with the lectures. We have gone through some introduction of vectors and tensors yesterday. So let me go to the lecture notes. So yesterday we did this particular lecture, and I believe we have gone through the point of defining what is a covariant vector. This is over here. Covariant vector having this transformation law with the inverse Jacobian, and then the example of this is the divergence of a scalar. And then another kind of vector is the contravariant vector, which is given by a very nice example is the tangent vector. Okay. And they both check. They both are one index, but the contravariant vector is the one with the upper index and covariant with the lower index, and they behave differently under the change of coordinates. Okay. And then we introduce the idea of a tensor product to build up tensors, the prototype of tensors. And then essentially, I think we have finished to the point of defining tensors in general, which are objects with a few, many index on the top and many index at the bottom. The number of index on the top tells you about the contravariant rank, and the number of index at the bottom is called the covariant rank. Okay. Okay, so let's move on. So the way we construct the tensors are using a tensor product. So you take two vectors and then you tensor product them. So essentially what happens in that particular case, the covariant vector and or the contravariant vector are essentially special cases of the tensors. They are tensors of rank 1. Okay. So what we did when we do the tensor product, we increase the rank of the tensor from 1 to higher. Okay. So the question is there any kind of operation that we can do for which we can actually, instead of making a higher rank tensor, we get a lower rank tensor? So this is possible, and we probably have this in different contexts. We probably have seen this in different contexts when we do summation of indices. So this is the summation of indices, generally called contraction. Okay, so let me just mention example over here, so that if I talk in general, probably you will not be able to imagine too much. But with this example, is you consider the case of a tensor of rank m, contravariant rank m, and a covariant rank n. Okay, and we take as an example, okay, without loss of generality, okay, we take the first index to be the same, the first index of the contravariant index, okay, on top to be the same as the first index at the bottom. And when we have a same index, we have to remember that we are going to sum over that index, and that index is a dummy index. Okay, so in other words, what we have effectively, the object that you have essentially is not of of m index at the top and n index at the bottom is actually m minus 1 at the top and n minus 1 at the bottom. Okay, so in other words, with this so-called summation of this first index on top and at the bottom, okay, essentially you are giving you an object and a tensor which has rank 1 less on top and rank 1 bottom. Okay, so in other words, what you get is a tensor of a lower rank as what we wanted. Okay, so initially it's supposed to be rank mn, so I'm going to just make this shortcut. This is the contravariant rank, and this is the covariant rank. Okay, so what we did was to contract one index at the top and one index at the bottom. Now, the example that we give here is essentially the first index, but it can be anywhere inside this row of index at the top and row of index at the bottom. Okay, so in other words, what we did was to create from this tensor of rank mn to a tensor of rank m minus 1, n minus 1. Okay, because this is a dummy index and the free index are just this one and this. Okay, so in other words, effectively we are creating a new object t tilde here with the free indices given by the ones which are not contracted. Okay, and one can actually show that this is indeed a tensor of lower rank m minus 1 and n minus 1. So if we just redo this in a different coordinate systems, so we take the dash, what you call the dash indices correspond to the dash coordinate systems, then the definition of this t tilde is given by this. Okay, so you just correspondingly write t alpha dash at the bottom. Okay, and then the rest is the free index. And then we start to replace this. You know how the upper indices are transformed. They are transformed using the Jacobian. Okay, so these are the Jacobian here. I think I missed something. No, it's okay. Oh, sorry. Okay, maybe I should not underline that. These are the Jacobian. Okay, the dash on top, and these are the Jacobian. And then these are the inverse Jacobian. Okay, so what we did here is, remember your alpha dash is actually a dummy index. So I have to introduce another index so that it gets contracted with the Jacobian. For example, here alpha dash beta, and for your alpha dash at the bottom, I will introduce another index gamma. Okay, so that it contracts with this gamma. Okay, and then you have your alpha dash over here, and then your beta and gamma will be beta and gamma at the moment is contracted over here. Okay, but essentially what happens here is that you see there is this alpha dash here and alpha dash here on the Jacobian and inverse Jacobian matrix. Okay, and that correspond to, if you want to write properly, I can write this way, so that it becomes adjacent. So it would be j gamma alpha dash and j alpha dash beta. So this alpha dash now adjacent to each other, and then this will actually gives you delta gamma beta. Okay, So by transferring the what you call the dummy index on the Jacobians, so to speak, we produce a Kronecker delta, which will now contract with this beta and gamma that we have introduced earlier. But then that will say that, okay, your gamma and beta must be the same, okay, because your Kronecker delta is equals to 1 if it's equal, but 0 if it's not. So in other words, what we have, we will now replace, let's say over here is gamma being replaced by beta. Okay, so that essentially is your contracted what you call tensor in the undashed coordinates, together with the Jacobians and inverse Jacobian. So here the inverse, sorry, this is the Jacobian. There are m minus 1 of them because it starts with mu2 dash, okay, and then over here is n minus 1. So in other words, this object, okay, under transformation to the dash coordinates will have this m minus 1 and n minus 1 Jacobians, okay. So that tells us, okay, this is just like m minus 1, n minus 1 rank tensor. Okay. So finally, that sort of proves that the contraction always give you in this particular case, you only contract once. You take a single one pair essentially. Take one pair. In this case, is the pair of the first index at the top and the first index at the bottom. But as I said, the index that being paired can occur anywhere. For example, it can be something like this: mu1 alpha dash dot mu(n), and then mu1 mu2 dot alpha dash. Okay, so it amounts to the same thing. You have contraction on both index. Sorry, this should be a dash, but it's okay. The idea is this is a dummy index, so you actually have three indices, which is n minus 1 here, and this is m, and n minus 1 over here. Okay. Now we can even do a contraction. Here is a contraction within the same tensor. Okay, in the same tensor. Now one can also do this the following, where you get two different tensors. Okay, for example here A and B. So if I were to think of this independently, so this will be a contravariant rank 3 tensor, and this will be a covariant rank 2 tensor. Okay, so in other words, what we have by taking all possible components of this, you get a new tensor, which is actually a product of these two tensors, which is rank 3, 2. Okay, so now with this rank 3, 2, essentially we can use the same trick as before. We take one of the index to be a dummy index on top and at the bottom. Okay, but effectively, since I know this object is coming from the different tensor, so it's really a dummy index on A and a dummy index on B. So remember, previously without the dummy index, we have a 3, 2 tensor, and over here, if you look at the free index on this object, it's just a 2, 1 tensor. Okay, and this 2, 1 tensor, you can think of contraction as before, or you can think of it as a tensor arising from contraction of a 3-0 tensor, okay, with a 0-2 tensor. Okay. So one can either think of it contraction happens within a single object, or you can do it with a different object. Okay. One of the things that we have actually seen is the following. It's a contraction between a covariant vector and a contravariant vector. So if you look at these indices that appear on this product, there are no free index. When there are no free index, that means there's zero index, that's a scalar. Okay. So, and we'll see that this kind of object is going to be, quite useful for us to actually do in special relativity. Okay. This is sometimes called an inner product between A and B. And remember that your A and B without the indices really, should be thought of as a vector geometrically, meaning it's pointing somewhere in space. Okay, and you can also think of it as, okay, if you remember in quantum mechanics, you have done inner product in the sense of taking a bra vector together with a cat vector. So you get a bra cat, okay? And over there, your bra vector is essentially a row matrix, and your cat vector is a column matrix. So what do you have? Say, maybe you can think of a row vector is given by an n by 1 by n matrix. 1 by n matrix to multiply with a column vector of n by 1 matrix, and that gives you a 1 by 1 matrix. So it's similar in this particular case. Okay. The other thing that one can actually make as if there's an intermediate tool to do contraction is the use of a Kronecker delta. Okay. So if I want to consider, for example, the earlier contraction between a covariant vector and a contravariant vector, I can think of this covariant vector independently of the contravariant vector, so meaning I have different index, mu and nu, for example, but then I insert, as a tool, I insert this Kronecker delta, which has this, the index mu and nu. So in other words, what happens over here is the fact that when this mu and nu are different, this will give you a 0, and the only way that you can have a non-zero answer is to have mu and nu to be the same, and effectively we get back to this idea of contraction between the covariant and contravariant vector. Okay, and you can do the same for any other what you call cases, like the one we had before is this 3-0 tensor with 0-2 tensor. Okay, so you can always introduce the contraction here, the sigma here, by this Kronecker delta. One can even also do the same with the fact of your t tilde earlier, something like this, sorry. Okay, mu2 until mu m, mu1 until mu n, which is really T alpha alpha thing. 2 mu m, mu1, un, but I can really think of this as what? Oh no, I cannot push this up because it's already end of the page. So I can really write this as alpha beta here, mu1, sorry, mu2 until mu n m nu 1, nu n, and I introduce again your Kronecker delta where I will have alpha beta here. Okay, so in other words, contraction is really can be demonstrated using this Kronecker delta. Okay, all right. Oh, there is enough space. Okay, never mind. Let me go down. Oh, that's it. So that's the last of this particular lecture. Right, it's too early to take a break. So let me just continue. Any question at this particular stage? I did mention yesterday, I think through the WhatsApp, that your notes are already for lecture 6 and 7 already uploaded this on the Putra Blast. So questions, anyone? No? Okay, so let me proceed. Oh, by the way, let me just mention this. I may finish early today because I would like to get some time to prepare for a talk I'm giving this afternoon. Okay, so let's see how far we get. Okay. This is essentially now we specialize to the case of tensors in special relativity. Okay. So in this particular all the thing that we need to do is to remember the previous lecture is essentially we talked about how tensors behave under, well, it's actually here, under general coordinate transformation. So I didn't specify how the transformation should look like, sorry. But in special relativity, our immediate concern is essentially how the coordinate transformation that we are of interest essentially coming from those coordinate frames of the initial frames, in special relativity. Okay, so these are essentially given by frames which are related to say the stationary frame by some linear transformation, and the linear transformation that we actually have seen earlier when we defined them is only of this particular form. Okay, where here you have your inhomogeneous part. So this sort of making translation of your origin of your coordinate system in space and time. But this part, you remember your L mu dash nu is a special kind of matrix called the Lorentz transformation. And you have the Lorentz your L, sorry, maybe I should write this instead. Your L mu dash nu obey Lorentz condition. Okay. So in other words, here we sort of go from the general case, okay, to a very special case for which it becomes quite simple, because essentially this is a linear transformation. So if I want to do the Jacobian, for example, I take partial x mu dash partial x nu, okay, on this equation. What's going to happen is it's just going to pick out this particular matrix of the Lorentz transformation. So in other words, your Jacobian now is essentially your Lorentz matrices. Okay, and your Lorentz matrices are just simply constants, they cannot depend on your x coordinates anymore because it's going to be linear. Okay, so these are constant metrics. This is a constant addition here. Okay, so that simplifies quite a lot. Okay, so now we'll be able to find any objects inside special relativity. Okay, most of the time we are going to limit ourselves to say a few index at the bottom or at the top. Okay, but generally we can have any index on top and bottom, meaning a general tensor, and how you transform will be just a transformation using the Lorentz matrices. Okay, and for those type of tensors which transform using the Lorentz matrices, we sort of specialize it to call to be specifically called a four tensor, referring to the four-dimensionality of space and time. Okay, this is not, of course, it's just a convention saying that, okay, when we talk about four vector, that means it's a vector in four-dimensional space and time, and essentially if it's special relativity, then it will transform according to the Lorentz transformation. Okay, so but generally your four tensors do not transform in the way we define this. The four tensors will not transform under the general coordinate transformation. If you want to do this, then you have a different theory. We call it the general relativity. What we are doing now is just a special relativity. So we're not doing general relativity. Okay? That would be a different course, which is not existent in UPM. Okay, but never mind. Maybe in the future. So, so one of the things that we're going to have is, for example, is the position four vector. We have actually sort of make the convention that your position four vector has to be a contravariant vector. Okay, so that means it's a single index at the top. Okay? So the relative position of four vector is is given by a position vector and then another position vector of fixed point, fixed event. So you take the relative position with respect to this fixed point. So if we look at this, how it transforms, okay, if we use the linear transformation earlier, okay, this one, then we have the following. This is for the x mu dash, and this is for the x naught mu dash, which is this one is a fixed event. Okay. So what happens in this particular case, the inhomogeneous part, the one with the constant addition, will cancel off. And then you're left with, okay, if you consider, for example, relative position with respect to a fixed point, usually you just take your fixed point to be the origin, okay, then your position vector is essentially a four vector, okay? A contravariant four vector. So in other words, now we will not consider the fact that you can have this, okay, because you always think in terms of a position relative to a fixed point. Okay. Now, earlier we have also introduced this idea of Minkowski metric. Okay, so Minkowski metric, what does it do? It gives you the length squared of your four vector. Okay. An example is this one, the s squared equals to eta mu nu dx nu dx nu. Okay, so your Minkowski metric as you can actually see, is really a 4 tensor which has covariant rank 2. Okay, and if you you already seen how the general rank tensor, how it behaves under coordinate transformation, then this one is again using the same thing, but in this particular case, what happens is that you can see that so remember, it's supposed to be looking like this, eta alpha dash. So I'm doing a different thing here. Eta alpha dash beta dash would be equals to eta, let me running out symbols now, gamma delta, okay, and then L alpha dash gamma, L beta dash delta. Okay, so this is essentially how we get the transformation law for covariant tensor of rank 2. Okay, so what happens in this particular case, this condition is the same as this condition, which is something that you have seen before. This is essentially the Lorentz condition. So if you, instead of using the dash coordinates appearing on the left hand side, you can make it the undashed coordinates appearing on the left hand side, and then you get this particular thing. I think I made a mistake somewhere. Oh, sorry, silly me. So if I really want the dash case, so I have alpha dash, beta dash. So let's put this as gamma delta. So I would have to have gamma, sorry about that, gamma here, so this will be a dummy index, but you need the free index here. So you have alpha dash L delta and beta dash. Okay, so that's the right one, sorry. So you can see this one is actually the inverse, because it's the inverse Lorentz transformation, or the inverse Jacobian if you want, corresponding to the covariant tensor transformation. Okay, so if you invert this, then you get the undashed coordinate on the left hand side, then you get essentially this. Okay, and that refers to the Lorentz condition that we had before. Okay. Okay, this is just saying the same thing. So if you remember the inverse transformation of over here multiplied with the Lorentz transformation over here, it should give you this Kronecker delta. Okay, and same thing here, the Lorentz transformation here multiplied by the inverse Lorentz transformation, and then you get again the Kronecker delta here. So if one actually, this is perhaps a proper way of introducing it. So what do? I multiply this on the left hand side. So in other words, I have to multiply that thing also on the right hand side over here. So this will now be contracted here. Okay. And then also this will contract with this. So you get that. And then essentially what you get is the Lorentz condition. Okay. Right. Okay. So this metric eta mu is a 4 tensor in special relativity. Generally, the Lorentz condition only works in special relativity. Okay. So in other words, if one has a general coordinate transformation for the tensors, then it won't obey the Lorentz condition anymore. Okay, right. Now we have introduced the metric earlier, eta mu, okay, which is essentially what I call a covariant tensor of rank 2. Now we would like to have something similar. So instead of a covariant 4 tensor of rank 2, okay, we want it to be a contravariant rank tensor of rank 2. Okay, and this should be when it multiplies this covariant 4 tensor of rank 2 of this Minkowski metric. Okay, then what's going to happen is that you should get the identity. Okay, this is a condition that we impose on this object, the new object eta mu nu here. Okay, so that it sort of behaves like an inverse of your matrix eta previously. Okay, so this as a matrix give you eta, so this one will give you eta inverse. So when you multiply both, you're supposed to get an identity. So when you multiply both, for example, remember the sum index will have to be adjacent over here. So eta mu rho, eta rho nu, and that will give you delta mu nu. Okay, so this is essentially in terms of matrices, this will be just the matrix eta inverse multiplied by the matrix in eta, and that gives you the identity. And we claim, or we propose, it's a proposition really, since eta mu nu, which is a Minkowski metric, is a covariant tensor of rank 2, then one expects this eta mu nu to be a contravariant tensor of rank 2. So all we need to do is just to show how it behaves under the Lorentz transformation. Okay, so what we do is just since we already seen how the this is eta mu nu, okay, your metric. Okay, so in terms of matrices, they are just given by that. So this dash thing is just saying that okay, we are considering the metric with respect to the dash coordinates. Okay, and that is equals to the Lorentz matrix transpose times eta, and then Lorentz matrix. Okay, that's your matrix equation of your Lorentz identity. Okay, so now what we do is simply to take this matrix equation and take the inverse. Okay, because we can actually prove it directly if you want. So I'll let you do this as exercise. Do this directly to prove it's a contravariant tensor. That means you have to show that it behaves under the coordinate transformation as a contravariant tensor of rank 2. Okay, here I'm just using the fact that I'm using the matrix equation. Okay, so the matrix equation, if you look at that, I take the inverse of this right hand side. Remember when you do inverses, you sort of alter the order of the matrices. So you get L inverse here from here, and then you get eta inverse, and then your L transpose inverse. And then essentially that translates to this. Your L transpose inverse is just L inverse transpose. And if you write down the components, it will give you this, which is essentially your transformation law for your contravariant tensor of rank 2. Okay, so that's more or less sort of said how with special relativity your metric tensor is a 4 tensor of covariant rank 2, and then automatically one should also have the inverse metric tensor, which is a contravariant rank 2 4 tensor. Okay. Now, as matrices, how do they look like? Well, you can easily, well, this one is from previous case that we have seen. It has to have this diagonal form. Okay, remember that this is coming from here, for example. And this is essentially what the x squared plus the y squared plus the z squared minus c squared dt squared. Okay, normally we put c equals to 1, so you get that. Okay, or you put x not x4, for example, we can put as ct. Okay, so that is the Minkowski metric that we have seen earlier. Then what is the inverse metric? The inverse metric is just the same matrix. Why? Well, if you multiply these two metrics together, you get the identity as you should. Okay? So in other words, the form of the matrix, with the matrix representation, you don't actually see the difference between the contravariant case and the covariant case. So, but you understand the covariant case and the contravariant case, they're going to behave differently under coordinate transformation. The only reason that you don't actually see this here is because your Minkowski metric is what we call a constant tensor. If it has some dependence on some coordinates, then it will be different. Okay? Usually this is actually done in general relativity. You have the metric tensor, which depend on the coordinates, but then the inverse metric will have a different what you call components inside it. Okay. One of the good thing for us to have a metric and also the inverse metric is to make it what you call as an operator in the sense that we can take a covariant vector and convert it to a contravariant vector. Okay, so how do you do this? So here is a particular case of a covariant vector. Okay, covariant vector A nu, and you multiply it with a inverse metric tensor. Okay, meaning this is contravariant tensor here, and we contract this with this covariant vector here. So you contract one of the indices, okay, nu here, and effectively the only free index is actually mu at the top, and we define this as the dual vector of this vector. Okay, so if you have a covariant vector for A mu, then the dual vector will be a contravariant 4 vector by the contraction of this inverse metric. Okay, and we use the same. Essentially, one could use a different symbol here. Okay, meaning maybe I write this as B mu instead, but we want to use the same symbol because they are somehow related to each other, so that you can say that this A mu is actually dual to this A mu here. And if you actually see what this contraction is supposed to be, you will find that, okay, it's all in terms of components of the vectors themselves, they are almost the same. Okay, your A1 at the index on top is equals to A1 index at the bottom, and the same thing for A2 and A3, but the only difference is this one, fourth coordinate. Okay, so the fourth coordinate will have a minus sign. Okay. Similarly, this is multiplying an inverse metric to a covariant vector. One can do a different thing. So this is what we call, here is called index raising. Okay, because why we raise this index to this index. We can do a different thing now by taking a contravariant vector. So this is contravariant vector, and then contract this with a metric tensor, which is a covariant metric. Okay, covariant tensor, sorry. So what's going to happen when you contract this, there will be an index, a free index at the bottom over here on both sides of the equation. That is essentially what we call the dual vector to this b mu is dual vector. Sorry, this b mu is dual vector to that. Okay, so it's just the same thing like before. Okay, so in this particular case, what happens is that this is a index lowering, and how you do you lower the index, you use using Minkowski metric. And index raising is using inverse Minkowski matrix. Okay. So now you can generate a lot of different things using this index lowering and index raising operation using the inverse metric or the metric itself. Okay. And you can see that if you do it twice, then you get back the same thing because you have this condition between the inverse metric and the metric. Okay. So now we can do this to any general tensor. So here is an example where I have this is a 1,2 tensor. Okay. Contravariant index 1, contravariant rank 1 and covariant rank 2. Convert it to a, in this case, it will be I'm doing the same thing. Okay, this will be again 1, 2 here, but I can do something different actually. But okay, the only thing that changes over here is the position of these indices. Okay, so sometimes we need to take note of this. Sometimes it doesn't make a difference, but in this particular case, to be more careful, one should actually take note of the indices. Okay. So here, if you look, the first two index here, okay, essentially the covariant index, and then your third index, your contravariant case, but the resultant that you get, the contravariant index is the first index. Let me try to make up some new thing here. Let me see. Let's do the same thing again. Let's do k alpha nu beta, and then I will just lower this thing down. So this will be beta rho, and then let me raise this index. Then this will be alpha here. Let's take a mu here. Okay. So what do I do here is essentially I'm going to raise this alpha index, and then I'm going to lower this index. So the resultant should be k mu nu rho. Again, it's a 1, 2 index. This is not what I want. Okay, this is the same. Okay, what am I doing? Let me do a different one. Okay, let's delete everything here. I want to do something different, so probably I don't want this. So let's do that. K alpha mu. Oh, I can do something like here. Okay, let's do this. Eta. So I raise it. So I have a mu, and then I also raise the new sigma here, and the resultant thing that you get is essentially K mu sigma beta. Okay, now it will be what? This will be a 3, 0 tensor. So I'm getting a 3, 0 tensor from a 1, 2 tensor. Okay, right. That's enough for the examples. So, okay, this is an important thing. So remember our inner product that we introduced earlier by contraction. So now we can do this explicitly. So we have an eta mu nu, a mu b nu, or we can write this as eta mu nu, a nu b mu. So here, what happens over here is I'm raising this index to get that, or I can lower this index to get this. Okay, it means the same thing. So you get the same thing, or you can also conclude that that this a mu b mu is the same with this a mu b mu here. It says the same thing. Okay, and when we write out what are the summation that's been involved, it actually gives you this a1b1 plus a2b2 plus a3b3 minus a4b4 by virtue of using either the inverse metric or the metric itself. Okay. Now, you remember in Euclidean case, for example, you have the idea of orthogonality. Okay, so when you take a dot product between two vectors, you know they are orthogonal if their dot product is equal to 0. We maintain that idea by saying that two vectors a mu, b nu, okay, is orthogonal if their contraction gives you the answer 0. Okay, and you'll find that this is actually this. So if you have two orthogonal vectors in one particular frame, it will always be the same, because really what is this equation say? This is a scalar. Okay, and the scalar is giving you the 0 answer. And since scalar doesn't actually change when you change reference frames, so this orthogonality condition actually works in all reference frames. So that's one thing that you can get from this. We can also take the inner product between a vector and itself, like this one. Okay, then essentially, like before, you'll get this sum of components here, but with a minus sign for the fourth one. Now, one of the things that we know, for example, if we take v dot v in the ordinary vector calculus, if it's equal to 0, then you know that tells us your v equals to the 0 vector. But in this particular case, it's not going to be necessarily a 0 vector. Okay, so if I have a mu over here, okay, gives you a 0, this is essentially what we call a like vector or a null vector. And that null vector doesn't mean that it has all components 0. Okay, it's a null vector saying that, okay, somehow when you add this thing up, okay, it gives you a 0 answer. And you can have that. What happens is that this positive quantity might cancel off this negative quantity. Okay, and another possibility, of course, this is this addition of squared terms may be more than this negative one. Okay, and that gives you this condition, and that condition is called saying that your vector is a space-like vector. And the final thing that we can also have is that this quantity is less than this quantity. So in other words, what you have is a mu is is less than 0. Then we call this as a time-like vector. So one of the properties that essentially one gets inside special relativity is this classification of vectors into 3 types of vectors. One is called the time-like vector, and the time-like vector appears inside. If you remember, we talked about light cones before. It appears inside the light cone, and the space-like vector appears outside the light cone, whereas the null vector or the light 4 vector appears on top of the cone. Okay, so why is this so? You consider, for example, the world line of a photon. World line of photon. So let's say let's have this to be, okay, I don't want to confuse everyone, so let's just use the axis to show the position of the photon as it propagates in time. Okay, what's going to happen in this particular case, this is ct squared, and the amount of distance, spatial distance that it covers will also be the speed times time. So this will also be ct squared. So in other words, we have ct squared minus ct squared, and that gives you a 0. So your world line of photon actually appears on top, well, on the light cone itself. So anything on the light cone is actually a null vector. Okay. So inside the light cone, then the thing becomes negative. This is less than that one. And outside the light cone, this one will be more than that one. Okay. So that is you'll see later on that yeah, I give you the assignment. Yeah, okay, maybe not. One of the things that one can have, for example, should I mention it now? Okay, your time-like vectors are essentially representing things for ordinary particles, for example. Okay, because ordinary particle will have speed less than c, so the distance it covers will be less than ct squared. Okay, and in other words, this will give you a negative world line. Okay, will be, so it could be actually not a straight line, it could be something like curve. Okay, but the curve will appear inside the light cone. Okay, and it has a slope steeper than the light cone. Okay. If you have a curve which has a slope less than the light cone, okay, then what can happen? Uh, this is sometimes called a tachyon. A tachyon is a uh, hypothetical particle with speed greater than c. Okay. Of course, you don't see tachyons in reality, but as a what you call a possibility in a particular theory, it is there. But if you have tachyons, the problem that you can actually get, you can send back signals, send signals to the past. And this would violate causality, and then you can signal to your grandfather, and then say do something so that I don't exist anymore, something like that. So you get your grandfather paradox and things like that. So in other words, what we have is now this good classification that actually tells you, okay, certain things are going to be restricted in special relativity. Okay. This probably will be, what's the time now? It's 10 o'clock. Let me see what else do we have inside here. Okay, maybe I can finish it. Right. So one of the things that we can also do, just now we talked about this scalar thing. Sometimes we can also have something like this. You have a tensor, and this tensor has all the components to be equal to 0. Okay, and this, you have to remember, this will refer to this undashed coordinates. So it will be referring to a particular reference frame for which all these tensor components are 0, but you can use the transformation law, and that also requires that in any other frames that these tensor components will also be 0. So in other words, tensor equations are going to be good because once it's valid inside one equation, it should be valid in other equations. Okay. So once it's valid in one reference frame, okay, then that equation should also be valid in the other reference frames. Take, for example, this equation. So this equation tells you about two different tensors here, T and S. You consider it totally independent of each other, okay? But somehow in one reference frame, they are equal, okay? Then I can rearrange this equation in this form, so I get the difference between these two tensors, the components of them, is going to be equal to 0. But then if I can do this, what does that say? I can also say this. So this will be in a different reference frame. So if I can say this, then it will also say that, okay, in this reference frame, the components of T and components of S also coincide. So that's the important thing about tensors in general, because when you write down equation involving tensors, one will work in one reference frame, then you know that it's going to work in all reference frames. And I have to say that this is with the condition that we are restricted to special relativity, because in general relativity that it can happen something else. Okay. And then once you have this idea, we can also have this kind of idea. We can talk about symmetries of a tensor. So consider this, for example. Here we talk about a tensor S, for which if you flip these two indices, it will give you the same thing. So this is symmetric tensor, and this is anti-symmetric tensor. Okay, so one can always do this, and this should in general also be true in all reference frame. The only thing that one has to be careful, okay, this works for the covariant case, it also works for the contravariant case. The only thing that one has to be careful is that if you try to do it for the mixed tensor, the symmetry may be destroyed by the Lorentz transformation, because you have this covariant and contravariant indices behaving differently. Okay. So these are rank 2 tensors. For example, here we begin with covariant rank 2, and then we can also do it for the contravariant rank. And then we did mention about the mixed tensor, which will not be true in general in terms of the symmetry. But what if there are a higher order tensor like this? Well, we can generalize again what we had for the rank 2 tensors. Okay, so we can consider what we call completely symmetric tensor, for which if you interchange any pair of these indices, they just give you back the same thing. Okay, so that's a completely symmetric tensor. Then you can also have a completely antisymmetric. So each time you interchange one pair of indices, it gives you a minus sign. If you interchange two pairs, then it gives you a plus sign, because each change gives you a minus sign twice, and then it becomes a plus. Okay, and then you interchange three times, three pairs, then it will give you back a minus sign. So this will be a completely antisymmetric tensor, and this should also be the case for all reference frames. Generally, we can form what we call a symmetrized version given a tensor. So what we do in this particular case, this is a shorthand notation to say that it's being symmetrized. Okay, this bracket here. What it does is to take all possible permutation of the indices and then sum it and then normalize it by 1 over n factorial, because that's the number of permutations that you can actually have. Okay, so this is, you can, for example, begin with something like T1, 2, 3, okay, and then you get the symmetrized, sorry, I should not specify that, say T mu nu rho, which could be not totally symmetric, but you can now symmetrize it, okay, by writing down all possible permutation. Okay, so 1, 2, 3, mu nu rho, and then mu, and so on and so forth. The same thing can be done also for the case of an anti-symmetrized version. So the difference between the notation of the symmetrized one, this is a round bracket, this is a square bracket. And how do you do the totally anti-symmetrized case is, again, you consider all the sums of the permutations of the indices, but each permutation, you have to see if it's an odd permutation, then you do a minus sign. If it's an even permutation, then you give it a plus sign. Okay, and then you sum it over, and then you normalize it by 1 over n factor. Okay, this operation sometimes is useful to define certain things in relativity, mostly general relativity, but no. again, this is a simple exercise that one can actually do. So sometimes, okay, you'll find odd things like this. Okay, I'm just giving you all the possible notation that you can actually see in a book. Sometimes you have the bracket actually is not over all the indices, but only on the three indices. That means it's only symmetrized with respect to these three indices, but not your mu1 and mu5 and so on. Okay. All right. Maybe it's time for me to take a short break. Is that okay? And okay, we'll take say 3 minutes break. Okay, can we restart? Okay, so let's move on. An important tensor which is totally antisymmetric is something that is analogous to your Levi-Civita symbol that we have introduced in Euclidean space. Okay, so we have a similar thing in this particular case for special relativity, and it's called an alternating tensor. Okay, so you have previously you remember is epsilon ijk thing. Okay, and this will be sort of dependent on the index 1, 2, 3. Okay, now with four-dimensional space-time, you have four index instead of three, so you get epsilon mu nu rho sigma. Okay, and we define this object to be plus 1 if mu nu rho sigma is an even permutation of 1, 2, 3, 4. Okay, and if it's odd permutation, then it will be a minus 1. Okay, so the definition is almost similar. Okay, and then if you have any other possibility, then you will have two of at least two of the indices will be equal, and that will be equal to 0. Okay, and the properties again is totally antisymmetric. So if we change any pair, so for example, epsilon rho nu mu sigma will be equals to minus epsilon mu nu rho sigma. Okay, so you change any pair of the indices, you will always get a minus sign. Okay, if you write down in terms of the components with specific mu nu rho sigma, then you have this thing, and you have to be careful. Over here, you probably don't have any more cyclic symmetry. Okay, but you have to actually check specifically whether it's even or odd permutation. Okay, and you know how to do this. One of the things that one actually has about your epsilon tensor, okay, your alternating tensor, is the connection with determinants. So in the case of a 3 by 3 matrix, for example, then you have epsilon ijk, and then L, sorry, I should use a different symbol. Epsilon ijk, M, I, L, M, J, M, M, K, N. That will be the same as determinant of epsilon. I should write this as L and N. Okay. If you have not seen this before, never mind, just take it for granted at the moment. But this now generalized to the case of the Lorentz matrix, which is a 4 by 4 matrix. So in other words, what we have is the following equation, analogous to this one. Then one could actually see for the case of your proper Lorentz transformation, okay, and proper Lorentz transformation has determinant L equals to plus 1, so this is plus 1. Then you'll see that this thing, so now this is just the number 1 there. This thing now will now behave as if it's a covariant tensor of rank 4, because you have this 4 matrices of your Lorentz transformation. Okay, so this is good because you can treat this as a tensor. But if you have things which is actually including the example is the boost, then you'll find that your epsilon mu nu rho sigma is not really a proper tensor, but it's sometimes called a pseudo tensor. Okay, so that's that. And another possibility is to have a different epsilon tensor, okay, a different alternating tensor, just like epsilon ijk in the case of the Euclidean geometry. You have epsilon ijk also at the top, okay, but in this particular case, these are actually equivalent in terms of definition, but it's not the case in the four-dimensional case, because what happens is that this will be multiplied by the to get this epsilon mu nu rho sigma on top. I will have to raise it using 4 Minkowski what you call 4 Minkowski metric inverse metric tensor, okay, and this has to be diagonal, if you remember. So 3 of them will appear for I equals to 1, or say for mu equals to 1, nu equals to 2, say rho equals to 3, and the last one has to be sigma equals to 4. Okay, you have no choice. So in other words, one of them will correspond to the fourth component, and that will be a minus 1. Okay, so when this becomes a minus 1 and the rest is 1, you get a minus sign. So you can see the difference now. The sign gets flipped. So if we remember our definition here is plus 1, minus 1, 0. Then the one with the top one will have this to be minus 1, this will be plus 1, and the rest is actually 0. Okay, so this is the definition. So that is with respect to the epsilon tensor. We don't have much problems with respect to this, but in certain cases we will need it when you doing certain identities, for example. And finally, I think, should I do this now? Or? If the final one will be with respect to some physical thing, but I wanted to finish before 10:30. Can I stop at this particular stage? If you don't mind, so that I have some time to prepare for my talk. Okay, so in that case, let me get your attendance first. Okay, that case, I would say thank you, everyone, and I will stop now.
Thank you, Doctor.
Thank you, Doctor. Thank you, Doctor.